The objective of this project is to examine the vibration characteristics of an aluminum alloy beam. We will discuss the theoretical predictions of the first three vibrational modes. Experimentally, we will determine the natural frequencies of the beam and capture the mode shapes. Lastly, we will compare the theoretical predictions to the experimental results. We begin with the Euler-Bernoulli dynamic beam equation. Because the beam is homogeneous, Young's modulus and the area moment of inertia are constant. It is assumed that material damping is negligible and that there are no external forces on the system. The equation is solved by assuming a separable solution for the beam displacement. By applying the appropriate boundary conditions for the cantilever beam, the trigonometric constant can be determined, which is used to solve for the natural frequencies of the system. At the free end of the beam, the moment and shear are both zero. The existence of natural modes is implied by the fact that the non-trivial solution only exists at specific frequencies. The mode shapes are the response of the system at each natural frequency. For this experiment, we used an amplifier, an accelerometer signal conditioner, a shaker with a beam and an accelerometer attached, a compressor, and a network signal analyzer. To begin the frequency scan experiment, we input a frequency range into the NSA. This outputs a sine signal to the amplifier at the desired frequency. The shaker converts the amplified signal to a displacement. To measure the vibration, an accelerometer is attached at the end of the beam. The SSC takes the accelerometer signal and performs data processing to output the frequency response. Lastly, this signal is sent to the NSA and recorded for further analysis. We know that at natural frequencies, the amplitude of vibration is greater than at other frequencies due to resonance. We performed a sine sweep from 1 to 350 Hz and plotted the frequency response. The natural frequencies of the beam correspond with the peaks in the frequency response plot. By scanning through the data imported from the NSA within the range of the three peaks shown, we can determine a local maximum which corresponds to that particular natural frequency. The local maximum in the range of the first peak is 12.41 Hz. The second peak shows a maximum response at 79.4 Hz. The third maximum is 234.5 Hz. We can excite the beam at these three frequencies to see the first three natural modes. Using the scanning vibrometer, we can capture a highly accurate and detailed description of the vibration of the beam and use that data to confirm the mode shapes predicted by the Euler-Bernoulli beam theory. For this portion of the experiment, we used an amplifier, a shaker with the beam attached, a compressor, a network signal analyzer, and a scanning vibrometer head and PC. To begin the mode shape determination experiment, we configure the NSA to output a sinusoid at each resonant frequency. This signal is amplified and then converted into a displacement at the shaker. At the same time, the NSA outputs the same signal to the vibrometer DMS. The output directs the vibrometer to scan the surface of the beam at an array of locations to measure the displacement. Lastly, the vibrometer DMS processes the output, displays the results, and records the data for further analysis. Despite small discrepancies in the natural frequencies, we find that the mode shapes are in very good agreement. The vibrometer data clearly shows nodes in the same locations as predicted by the theory. This is especially evident in the second mode, where we can see fixed points at x equals 0 and at x equals 4/5 the length of the beam. The numerical solution to the governing equation is very sensitive to the length of the beam. This presents a large source of error for this experiment, especially since the boundary at x equals 0 is not a true fixed boundary, but instead is a fixed area in the center of the beam. We note an interesting phenomenon in the frequency response that is not predicted by the Euler-Bernoulli theory. An anti-resonance occurs near 140 Hz that is a result of a plate mode. There is a node at the same location as the accelerometer.